This resource gives a number of worked examples demonstrating the product rule. So previous videos have given a definition and a concise derivation of differentiation from first principles, and the aim now is to give a number of worked examples. It's normal, once the derivations are understood, to actually use a table of known results, that is, not to derive simple derivatives from first principles. So here we're going to show how a table is used in combination with the product rule in order to differentiate functions which are products of other functions. The product rule says that if you have y and it's defined as u of x times v of x, so the product of two functions, then dy dx is u times dv dx plus v times du dx. So all we're going to do in this video is illustrate the use of this formula. Now you're reminded that you're expected to use a table of common or well-known results, and these are readily available in many places, so I'm not going to go through these results. I've just displayed them here as an indication of the sorts of results we might call upon. Technique then. This is really important. You need a good technique once you start dealing with things like the product rule, because otherwise your page will get very messy. So the first thing to do is define all functions used in the product rule with their associated derivatives clearly. So give yourself a good space on the piece of paper and define them clearly. Ensure the layout of your work is uncluttered and unambiguous, and that will help you avoid making typographical errors. And wherever possible, use known results from a table rather than deriving them. So here's an example. We want to differentiate f of x, which is 2x cubed times cos 4x, and we can see this is a product of two functions, so we've put up here, we know we're going to need to use this product formula. Dy dx is v du dx plus u dv dx. So my first job is to define a suitable u and a suitable v. So here what I'm going to do is define u as 2x cubed, and therefore du dx, using the result in the table, which I'm not going to redo because that was in the previous resource, is going to be 6x to the 5. I'm going to define v as cos 4x, and again, using the result in the table, the derivative of this is minus 4 sine 4x. And now all I do, you'll see that I've got these four values nice and neatly defined. I just need to plug them into this formula here. So I'm going to write dy dx equals, so if I do the v first, cos 4x, and that multiplies by du dx, which is 6x to the 5, and then plus, I do the u next, which is 2x cubed, and that's going to be multiplied by dv dx, which is minus 4 sine 4x. And there's your answer. Okay, example 2. Find the derivative of the following, and you'll see again this is a simple product of two smaller functions. So my first job is to define u and v and the associated derivatives. So here I'm going to define u equals 2e to the minus 2x. So again, using the table, which I'm not going to go through because that was the previous video, I'm going to get du dx is minus 4e to the minus 2x. And then v I define as tan 3x. So again, using the table, dv dx is going to be 3 sec squared 3x. Oops, sorry, I didn't mean to skip then. And so now all I do is plug these values into the formula. So dy dx is going to be v, which is tan 3x, times, I'll put brackets there to make it clear, so tan 3x times du dx, so that's minus 4e to the minus 2x, and then plus u, which is 2e to the minus 2x, times dv dx, which is 3 sec squared 3x. And hopefully you're getting the viewpoint that this is straightforward as long as you're neat and tidy. Keep nice clear definitions of u, du dx, v, v dx, make sure they're obvious, and then you just have to plug them straight into the formula. Example 3. Find the derivative of f of t equals minus 4t log t squared. So again, first job is to define u and v, du dt, dv dt. So here I've defined u as minus 4t, and therefore du dt is going to be minus 4. I've defined v as log t squared. Now just in case you're not sure, remember this can be written as 2 log t, and you'll find log t in the table, so dv dt becomes 2 over t. So now all I do is take these values and plug them in to the formula. So dp dt equals v, which is, I can write log t squared, or I could write 2 log t, it doesn't really matter. So I've got log t squared, that's v times du dt, which is minus 4, and then plus u, which is minus 4t, times dv dt, which is 2 over t. You'll notice I'm not trying to simplify these expressions because that's not the purpose of the video. Example 4. Here we're going to need to use the product rule twice, because what you'll notice is I've got 1 function, 2 functions, 3 functions. So what I'm going to start by doing is joining these 2 functions together and calling them u. And then the other function I'm calling v. So my starting formula is dh dw equals v du dw plus u dv dw. So I know where I want to get. So my problem is that I know u is w squared e to the 3w, but where am I going to get du dw from? So I'm going to have to use the product rule on this. So here I've written it down because I'm a bit more experienced by inspection. I've said that du dw is going to be e to the 3w times d dw of w squared plus w squared times d dw of e to the 3w. And you'll notice what I've done is I've used the product rule directly on this formula, and as you get more experienced you'll be more comfortable just doing that by inspection rather than having to lay out a whole page. So if I write this one out, you'll see what this reduces to is 2w e to the 3w plus 3w squared e to the 3w. So now this is du dw, which I can plug into this formula here. I've got u, which I can plug into this formula here. So all I need to do is finish off with what was v. Well, v was sine 2w, so dv dw is 2 cos 2w. And I know this is beginning to get messy, but let's see if we can try and fit it in. So eventually then dh dw is going to be v, which is sine of 2w, times du dw, which is 2w e to the 3w plus 3w squared e to the 3w. And then we get plus, and then it's u, which is w squared e to the 3w times dv dw, which is 2 cos 2w. And you'll see it's not actually that difficult if you keep a clear head. But this is a case where I've had to use the product rule twice. So in summary, this video has demonstrated the differentiation of commonplace functions using a lookup table in combination with the product rule. And viewers will see the steps are largely mechanical as long as you're neat and tied. Yes, they can be a bit tedious, that's one of those things, but they're not too difficult as long as you keep your page well organized. Keep clear definitions of u of x and v of x and their derivatives before substituting into the formula, unless you're a bit more confident, and then you might be able to write the expression out by inspection. In general, it's advisable to have a lookup table to hand, even though in due course you're likely to remember many of the results.